So in today's lecture we are going to continue with maxima minima again. The aim is to get an analog of the second derivative test. So we start with the extended mean value theorem, what we have proved in the last lecture. It says that if x naught is the point x naught y naught, f is a differentiable function, and let us say x is given by xy, then I have that f of x equal to f of x naught plus x minus x naught times fx plus y minus y naught fy plus the extra terms are half x minus x naught square fxx plus 2 times x minus x naught into y minus y naught fxy plus y minus y naught square fyy. This is at a point C, where C is a point on the line joining x and x naught. Okay, so this was the extended mean value theorem. The way we have written it now, which is useful for us, that let us say Ax is x naught plus h, y naught plus k, then f of x naught plus h, y naught plus k, that is equal to f of x naught y naught plus hfx plus kfy at the point x naught y naught plus half h square fxx plus twice hk fxy plus k square fyy. Okay, this we have proved in the last lecture. Now, about existence of maxima minima, we are going to use a theorem without any proof, but this is analogous to the one variable case, that if you have a continuous function on a closed interval, closed and bounded interval, then the function achieves its supremum and infimum on that interval. That is, the maximum and minimum of the function exist in that interval. So there exists an analogous theorem here, that suppose if f from R2 to R is a continuous function, then f has maximum and minimum in any closed and bounded region omega. Okay, so you take any closed and bounded region omega. Bounded means it can be put inside a disk, and suppose f is a continuous function from here to R, then maximum and minimum of f has to be there in omega. Now our aim is to get hold of maximum and minimum if they occur in the interior of omega. So for that I need the definition of interior of omega. What do we mean by interior of omega? It means, suppose x naught y naught is a point in omega. If there exists a disk D containing x naught y naught and D is a subset of omega, then x naught y naught is called an interior point. So, for example, suppose this is my omega, okay, the boundary points included. Then if I take any point here inside, I can put a small disk around that point which is inside the square. But if I take a point here on the boundary, then whatever disk I choose, it goes out of omega. So the points on the boundary of this square are not interior points, but the points on the square which are not boundary points, they are interior points. So our viewpoint is that when any point in the interior is a maximum or minimum of a function, that I want to find out. Okay? So our aim is to find out local maximum or local minimum of a continuous function f in the interior of omega. Okay, so you start with back calculation. So let us say x naught y naught belongs to interior of omega. Okay, then if x naught y naught is an extreme value, that is either it's a local maximum or a local minimum, then the partial derivatives has to vanish. This would imply that fx at x naught y naught, this is 0, okay. Now I apply the extended mean value theorem. That would give me that f of x naught plus h, y naught plus k, that is equal to f of x naught y naught plus half h square fxx plus twice hk fxy plus k square fyy at a point C, where C is the point okay. So if I take this point to be x naught y naught, suppose this point is x naught y naught, then if I look at any points here, they are of the form x naught plus ch, y naught plus ck, if this point is x naught plus h, y naught plus k. So by varying hk and c, I can actually get hold of points in a disk around x naught y naught. That is the whole point. Okay. Notice in the above expression, the fx and fy's don't appear because fx and fy are actually assumed to be 0, because x naught y naught is supposed to be a local extremum, that is either a local maximum or a local minimum. Then what we do is that this implies f of x naught plus h, y naught plus k minus f of x naught y naught. I just write this as half. That means I am just taking one thing from the other side of the equality, this is h square fxx plus twice hk fxy plus k square fyy. Okay. Now what I do is I multiply both sides of this equality with fxx. Okay. So now I am going to concentrate on the right hand side. So what it is half h square plus k square fxx into fyy. Okay. This can be written again as half h square fxx square plus twice hk fxx into fxy plus k square fxy square minus k square fxy square, then plus the remaining term k square fxx times fyy. Now the first terms together, they form a whole square, so I get h fx plus k fyy whole square minus, I would write it at plus k square fxx fyy minus fxy square. Okay. So this is the difference. So let me denote this as q xy So in a nutshell, what I have is f of x naught plus h, y naught plus k minus f of x naught y naught times fxx at x naught y naught equal to q of. Now q being a continuous function, if it is bigger than 0 at some point x naught y naught, or it is less than 0 at some point, that means in a disk around that point the function is bigger than 0 or less than 0, just like one variable continuous functions. What does it say? In one variable, if I have a continuous function f which is bigger than 0 at a point, then there exists an interval around that point where the function is positive. Similarly, the same logic applies in two dimension, that if I have a function f continuous and positive at a point x naught y naught, then there exists a disk around that point where the function is positive. The same thing works for negative. And since I am assuming that all the partial derivatives which exist here are continuous, I will get my function q also to be continuous. Okay? And hence if it is positive at some point, it is positive in a neighborhood of that point. Now the whole issue is that given a point x naught y naught, whether the function is a local maximum or a local minimum. Now notice, suppose x naught y naught is a local maximum. That means f x naught plus h, y naught plus k must be lesser equals to f of x naught y naught, because f of x naught y naught is local maximum. Okay. Now that will be reflected on the sign of the function q and the sign on the function f of xx, because f of xx is multiplied here and this function I have here. So under what conditions, using signs of fxs and q, I can impose certain sign condition on this portion. That is the whole issue now. Okay. So let me attack that problem now. So I consider q x naught y naught, this is half h fxx plus k fyy square plus k square into fxx okay. So and I also have that 2 times then fxx well, this expression which I have written here is, it is multiplied with fxx at x naught y naught. So fxx at x naught y naught times q x naught y naught is actually this quantity on the right hand side. Okay. Now because of this now I have that fxx at x naught y naught times this is okay. Now notice that this quantity here is always bigger than or equal to 0 because it's a perfect square. So there are several cases. Now let me look at that. Suppose fxx at x naught y naught is bigger than 0 and fxx fyy minus fxy square, sorry I don't have square here, what I have is, and suppose this quantity is at x naught y naught strictly bigger than 0, then of course in a neighborhood of x naught y naught both the functions are bigger than 0. So this would then imply that q of x naught y naught is bigger than or equal to 0, because q of x naught y naught, if I look at, that gives me just this whole square quantity plus k square times the object. So this whole quantity then is bigger than or equal to 0. That would then imply that f of x naught plus h, y naught plus k minus f of x naught y naught, this is bigger than or equal to 0. Because let me look at this expression which I had here, that this quantity was this that we have shown, then this was multiplied with fxx times x naught y naught, this was then multiplied with fxx at x naught y naught. Okay. Now this multiplication on the right hand side produced a whole square plus some term. the term which I got exactly, I have written it down, it is this term, okay, after multiplication. So when this quantity, if this quantity is bigger than 0, then the whole thing is strictly bigger than 0. Fine. Now we go back again. That means this whole right hand side here, what I got, this is strictly bigger than 0. Now I am also assuming that this is strictly bigger than 0. That would certainly imply that the quantity I have here, this portion must be strictly bigger than 0. Okay. That means what? That means f of x naught plus h y naught plus k is always bigger than or equal to f of x naught y naught in a neighborhood of x naught y naught. That means in a disk around x naught y naught. That means f of x naught y naught must be a local minimum. So the conclusion then is that x naught y naught is a local minimum. Then the next case, assume now that f of xx at x naught y naught is less than 0 and fxx fyy minus fxy square at x naught y naught is strictly bigger than 0. So I again write down that f of x naught plus h y naught plus k minus f of x naught y naught, this times fxx at x naught y naught. I know what this quantity is. This is half h fxx plus k fxy square plus k square times fxx fyy minus fxy square. Now I am assuming that this is positive, but I am assuming that this is negative, this quantity. Putting together, since this is always bigger than or equal to 0, this quantity. Putting together these three facts, what I get is that this implies f of x naught plus h y naught plus k minus f of x naught y naught, this is less than or equal to 0. This implies then that x naught y naught is a local maximum, because x naught plus h y naught plus k represents points in a disk around x naught y naught, and from my conditions I can see that in all points in a disk the value of the function is less than or equal to the value of the function at x naught y naught. That means the value of the function at x naught y naught is larger than any other value in the disk. That means it's a local maximum. Okay. So let us summarize what we have got so far. So for that I need a notation. I define, let us say, B equal to this matrix of double partial derivatives. Okay. Now then my condition 1 was, let us have a look at it again. The condition 1 was fxx is bigger than 0 and this quantity is bigger than 0. So if fxx at x naught y naught is bigger than 0 and fxx fyy minus fxy square at x naught y naught is bigger than 0, then x naught y naught is a local minima. So just look at this formal matrix which I have written. If I formally calculate a determinant which I would call D, that is precisely fxx fyy minus fxy square. So all we are saying is that D at x naught y naught is bigger than 0. So it can also be written as D at x naught y naught is bigger than 0. Then I got the second condition, that if fxx at x naught y naught is less than 0 and fxx fyy minus fxy square at x naught y naught is bigger than 0, then x naught y naught is a local minima. Okay. Now problem starts when D is equal to 0 or D is less than 0. Now in those cases we are not going to prove anything. I will just let you know what exactly happens in those cases. There is not much to say about those cases, and then we will go to some examples to see how do one apply these results to characterize maxima and minimums. Now the third case, I am not going to prove anything here, that suppose fxx fyy minus fxy square at a point x naught y naught is less than 0. Notice in the previous case, everywhere I have looked at this quantity is bigger than 0, this quantity is bigger than 0. I never looked at the case less than 0, which I am going to do now. Suppose it is less than 0, then it turns out that x naught y naught, this point, is neither a maximum nor a minimum. What happens is, then there exist arbitrary small disk around x naught y naught where there exist xy such that fxy is bigger than f of x naught y naught and f of x prime y prime, that is some other point will remain in that neighborhood where this happens. That means when D is less than 0, one can actually show that there exists arbitrarily small disk around those points such that in those disks there are points xy and x prime y prime such that f at xy is bigger than f of x naught y naught and f of x prime y prime is less than f of x naught y naught. That means this point x naught y naught is neither a local maximum nor a local minimum. Okay, we will see examples of such kinds. Now this kind of points are called saddle points. So saddle points are points for which of course fx and fy turn out to be 0, but when I look at fxx fyy minus fxy square times x naught y naught at x naught y naught, that turns out to be negative. These are called saddle points. So the quantity D which I had written down at x naught y naught, that turns out to be negative. Those are saddle points. Fourth is what happens if D is equal to 0. We will see in examples that this means the test is inconclusive. That is, if this quantity turns out to be equal to 0, then you just cannot say anything. So what are the favorable cases then? That you look at first, so what is the strategy of proving getting maximum minimum is simple. First you look at the partial derivatives. So let me explain it here. What is the strategy? First look at all xy such that fx equal to 0 equal to fy. That is step 1. Collect the zeros. What you get are called the critical points. After getting those points, there are two things you need to do. First look at this quantity, fxx, fyy minus fxy square. Okay, see whether it is bigger than 0 or less than 0 at the critical points. At the critical points. Third step is, if fxx fyy minus fxy square at xy, that means at the critical points, if it is bigger than 0, check what about fxx, bigger than 0 or less than 0. Depending on that I will get, if it is bigger than 0 then I get minimum, if it is less than 0 I get maximum. While checking D, if it is bigger than 0 then I will proceed, if it is less than 0 then saddle point. If D turns out to be equal to 0, then none of these things will help you. You have to look at the function and try to see whether you can find out maximum or minimum. The double derivative test essentially fails if D is actually equal to 0. Okay? So now slowly let's turn on to some examples where these methods will be described to you. Let us look at our first example. Suppose fxy equal to xy. So first I have to search for critical points. So fx is y, fy is x. So what are the points where both fx and fy are 0? The only solution is the point 0, 0. So 0, 0 is the only critical point. Then I have to search for D, capital D, that is fxx, fyy minus fxy square at the point 0, 0. So I need to calculate what is fxx. Fxx turns out to be 0 because fx is a function of y only. What is fxy? That also turns out to be 0. No, fxy turns out to be 1. And what is fyy? Because fy is a function of x only, so fyy is 0. This implies D is equal to minus 1. So this implies, in this case 0, 0 is a saddle point. Can I see that it is a saddle point? That is, in arbitrary small neighborhoods of 0, 0, the function takes value bigger than f0, 0 and less than f0, 0. Now what is f0, 0? That is 0. So in 2 dimension, this is the point 0, 0. I take any disk around this. If I take a point here, then x and y both are positive. So fxy is bigger than 0. If I take a point here, then x is positive but y is negative. So fxy is less than 0. But this 0 is actually f of 0, 0. So you see that around any small disk about 0, 0, whatever disk I choose, I can get xy where the value of the function at xy is bigger than f0, 0, and points where the value of the function at 0, 0 is at xy is less than f of 0, 0. So this justifies why this is a saddle point. Okay. Now let us look at our second example. Now let us look at this function f of xy equal to 4xy minus x4 minus y4. I want to check for maxima minima of this function. So I start again with partial derivatives. What is fx? It is 4y minus 4x cube. What is fy? That is 4x minus 4y cube. So now I have to solve fx equal to fy equal to 0. This implies 4y minus 4x cube equal to 4x minus 4y cube. From this it implies that the only critical points you can get are 0, 0, 1, 1 and minus 1, minus 1. These are the critical points. This is easy to check. Now once I got hold of the critical points, I have to go to the next partial derivatives. That means now I need to calculate what is fxx. Well, fxx turns out to be minus 12x square. What is fyy? That is minus 12y square. Then what is d? That is fxx into fyy. So it is 144 x square y square minus, now I need what is fxy. Well, that is easy to calculate. fxy is 4. So it is minus fxy square, that means I get 16. See, fx is 4y minus 4x cube. So what is fxy? I have to differentiate it with respect to y. What I get is 4. But in d what appears is fxy square. So I get 16. Now I will check. Now at 0, 0. So this d is certainly less than 0 at 0, 0. So this implies the point 0, 0 is a saddle point. Now what happens at 1, 1 and minus 1, 1? Now if I put x and y both to be equal to 1, then d is positive. So d is bigger than 0 actually at 1, 1 and minus 1, 1 both. Since in the expression of d I have a square in x and square in y, it doesn't matter whether I put plus 1 or minus 1. So in any case I get d to be positive. Now what remains to check is what happens to f of xx at 1 or minus 1. Now you look at the expression of f of xx, there is no y involved, only x, and that is square. So if I put x equal to 1 or minus 1, it doesn't matter. Whatever you put, you get that fxx is equal to minus 12. And this is also minus 12. Both are less than 0. So d is positive, but these quantities are less than 0. So finally what is my result? The result is 0, 0. This is a saddle point because d there is negative, and 1, 1 and minus 1, 1, these are local maximum. Okay, fine. So this is, the method is slowly getting clear what exactly you need to do. You first look at the partial derivatives, find the critical points. At the critical points you check the d the sign of d first. If it is negative, then you already know that it's a saddle point. But if it is positive, then you have to check fxx and try to see what happens there. Now let us look at our third example. The function here is fxy equal to x cube minus 3xy square. Okay. So again we start with fx. Fx is 3x square minus 3y square, which is equal to 0, I have to see, and then fy, that is minus 6xy, that is equal to 0. So if I try to solve this, this implies the only critical point which comes here is 0, 0 is the only critical point. Now I have to see the behavior of the critical point 0, 0. So for that, first I have to start with d. So I need to know what is fxx. Fxx turns out to be 6x. What is fyy? That turns out to be minus 6x. And then I have to look at fxy. That is minus 6y. Okay. Now, if I look at the point 0, 0, then all these quantities are actually equal to 0. So this implies d, that is equal to 0. So let us check our calculation again. Fxx means what? I have to differentiate the function fx with respect to x. I get 6x. Then I look at fyy. So this is a function minus 6xy. I have to differentiate it with respect to y. I get minus 6x. Then I have to look at fxy. So for that, what I do is I look at the function fy and differentiate it with respect to x. I get minus 6y. So this implies d is equal to 0, because fxx into fyy at the point 0, 0, that is 0, minus fxy square, but at the point 0, 0 fxy is 0, so its square is also 0, so as d is 0. So the double derivative test cannot be applied. So question then is, what is the behavior of the point 0, 0? Well, what I do is I just assume y equal to 0. Okay, that means I am looking at the behavior of the function only on the x-axis. Okay, because y I am taking to be 0. But then what is fx0? That turns out to be equal to x cube. Okay, then I can certainly see that fx0 is bigger than f of 0, 0 if x is bigger than 0, and it is strictly less than f0, 0 if x is less than 0. That means if I am concentrating around any disk, and any disk around 0, 0, then the points here gives me f of xy bigger than f of 0, 0. But if I am looking at points here on the left hand side, then f of xy is less than f0, 0. What is the conclusion then? It means 0, 0 is actually a saddle point, because in every neighborhood or a disk around 0, 0, there are points xy where the value of the function is bigger than f0, 0, and there are points where the value of the function is less than f0, 0. So this implies 0, 0 is a saddle point. Notice that this conclusion we have drawn not by the second derivative test, by analyzing the given function. Since the function was of a particular form, the function is of this form, I have exploited the form of the function to achieve that 0, 0 is a saddle point. The conclusion did not follow from the second derivative test, because second derivative test, if you want to apply, then at the critical points d must be bigger than 0 or d must be less than 0. D bigger than 0 might give you maximum or minimum. D less than 0 will give you saddle point. But if d equal to 0, then the second derivative test does not say anything. So we have to use some trick there when d is equal to 0 to check what is the nature of the point. In this case in particular, we have gone through a particular axis and checked that 0, 0 is a saddle point. Okay. Let us go to our next example, the last one. I look at the function fxy equal to 3x to the power 4 minus 4x square y plus y squared. The first thing I want to show is that f has local minimum at 0, 0 along every line through 0, 0. Okay. This is a line, this is a line, this is a line. So I am going to check. So what I do is, first I go through lines y equal to mx. Okay. The only line which I have here which is not of this form is the y-axis. So for that one needs to do separately the checking that 0, 0 is maximum. That is, you just put y equal to 0 and then check what happens. Well, you look at the function. If you put y to be equal to 0, the function you get is fxy equal to 3x to the power 4, which has certainly minimum at 0, 0. So it is the other lines which I am looking at. So if I put y equal to mx, then my function, if I call it gx, that is 3x to the power 4 minus 4mx cube, I am putting y equal to mx plus m square x square. To check that 0 is the minimum, now I can use the one variable theory which I have at my disposal. So g prime x I look at, that is 12x cube minus 12mx square plus twice m square x. Okay. So this certainly means that 0 is a critical point because I can take x common. So then I look at g double prime x, that is 36x square minus 24mx plus twice m square. So this implies that g double prime at 0 is twice m square, which is bigger than or equal to 0. This implies x equal to 0 is a local mean, and hence 0, 0 is a minimum of the function along the line y equal to mx. As we have already noticed that if I go through y-axis, then obviously 0, 0 is a local minimum because my function is thrice x to the power 4. The minimum value is always at 0, 0. But question now is, is 0, 0 a local minimum? What is the point of asking this question? Well, the point is this. Let me draw a bigger picture. Suppose I look at a disk around 0, 0. Then I look at all the points in this dotted line. Then I have checked that f of 0, 0. So if xy is here, this implies f of xy is bigger than or equal to f of 0, 0. Okay. If I take this dotted line, then I might get another disk where f of 0, 0 is less than all the points on this line, the second dotted line. But the question is 0, 0 a local minimum? That means, can I say that there exists a disk around 0, 0 such that for every point in this disk, f of x, y is bigger than or equal to f of 0, 0. See, do you understand the question here? Because when I look at a line, then 0, 0 is a local minimum means there exists an interval on which f of 0, 0 is the minimum value. But depending on the line, the interval changes. But here what I am asking is that can you find a disk such that in that disk, for all the points xy, f of xy is bigger than f 0, 0? Well, we will see that the answer is not true, that 0, 0 is not a local minimum. What I do is, I write down the expression of fxy again. I know the expression, it is 3x to the power 4 minus 4x square y plus y squared. I write it in the form 3x to the power 4 minus 3x square y minus x square y plus y square. Then I take 3x square common, I get x square minus y. I take minus y common, I get x square minus y. So the function is x square minus y into 3x square minus y. Okay. Now again let me draw a picture. What I do is, I draw the curve y equal to x square. Okay. So when I draw the curve y equal to x square, it looks like this. This is the curve y equal to x square. Now let me draw the curve y equal to 3x square. That will look like this. This is y equal to 3x square. Okay. Now suppose I am searching for a disk, so let me draw a disk. A disk around 0, 0 looks like this. Now in all these disks, does not matter whatever radius you take, these regions 1, 2, 3, 4, 5, 6, these 6 regions are always there in the disk. Okay. Now suppose I choose a point x here. Suppose xy belongs here. Then I know that y is bigger than x square and y is less than 3x square. This then would imply that x square minus y is less than 0 and 3x square minus y is bigger than 0. This would imply then that f of xy, which is product of this, one is positive, other is negative, is less than 0. But notice this 0 is actually f at 0, 0. So I get a point in the disk where f of xy is less than f 0, 0. Okay. But what happens if I choose a point here? Suppose this is x prime, y prime. So for that point, what I have is that y prime is bigger than 3x prime square and y prime is bigger than x prime square. This implies 3x prime square minus y prime is bigger than 0 and x prime square minus y prime, this is bigger than 0. This together would imply that f of xy now is positive, bigger than 0, but that is f at 0, 0. Okay. That means what? That means whatever disk I choose, I get another point x prime y prime where f of x prime y prime is bigger than f of 0, 0. That means in arbitrary small disk around 0, 0, I get points xy such that f of xy is bigger than f 0, 0 and f of xy is less than f 0, 0. What does it mean? It means 0, 0 is a saddle point. So notice something nice has happened here, that the point 0, 0 along every line, then I can think of f as a function of one variable. In that case, 0, 0 is a local minimum. for every line. But in the sense of two dimension, when instead of intervals you think about disks, in that sense 0, 0 is not a local minimum, it is a saddle point. Okay, this is happening simply because instead of intervals, now by neighborhood I mean disk. So you are demanding more, and that is why this problem is happening. Okay, so we will stop at this. This is the way one should go about finding the maximum minimum using the test of double derivative. The thing to remember here is that the most fundamental thing is first checking the critical points, which you get by equating the partial derivatives to 0. Now, whether these critical points give you maximum or minimum depends on whether your D is positive. If D is positive, then you can start checking whether it is maximum or minimum by going to fxx. But if D is less than 0, you know certainly it's not a maximum or minimum, it's a saddle point. The most problematic case is when D equal to 0. Then you have to look at the given nature of the function and you have to do something to see what is the nature of the function. So we have seen some examples where we have always exploited the nature of the function to determine what is the nature of the point. So that is all for maximum and minimum. In the next lecture, we will go to another important problem called the method of Lagrange multipliers.